Okay, we'll try to look at problem 3.14. Okay, the current through a 0.5 microfarad capacitor C is equal to 0.5 microfarads. Is shown in figure 3.14. So they have capacitor here, and this is the voltage V of t, and this is the current I of t flowing into the capacitor, and the capacitor is 0.5 microfarads, and they're saying that the current through the capacitor looks like this. So this is I of t in milliamps. So this is 20. This is after 2 seconds, 3 seconds, 3 milliseconds. Sorry, this is time. Also in milliseconds. 2, 3, and this is 5, and this is minus 20. Okay. At t equals 0, the voltage 0. So this is t in milliseconds, but this is v of t, and at t equals 0, the voltage is 0. They tell us that. Sketch the voltage. They want v of t. They want power, p of t, and stored energy versus time. Okay. So let's start with, first things first. So we have some relationships that govern capacitor and current and voltage, right? So IC is equal to C dVc of t by dt. V of t, if we want to find the voltage, is equal to 1 over C, the integral of IC of t dt plus the initial conditions. I'll call this I0. So now we should be able to draw the voltage, theoretically speaking. Plus V0, sorry. It's initial condition, so I should have just said IC. Initial condition. So it's, in this case, yes, it's the initial condition for voltage. Initial condition for voltage in this case is 0. Now it's 0, right? So now it's 0, and then voltage will be equal to the integration of current multiplied by a scaling factor. Okay, so this is the current waveform. So let me draw these things here, right? And what is the integration of a fixed quantity? A ramp, right? The integration of a fixed quantity, so integration of 5 dx is equal to 5x, right? So it's a ramp, right? And this ramp starts from initial condition of 0. So I will have a ramp here starting from 0 going to some value. We'll have a certain slope. This slope is dictated by these numbers. We will look at the numbers, okay? So, and then what? In this zone, its current is 0, so there is no increase or no change in the voltage since the current is now 0. So this is 0, but our initial condition exists because we have an initial condition for voltage for this second phase. So we look like this, right? And then now our new initial condition is this point here. And an integration of a negative number is a negative ramp, negative slope. So it would be like this. If we go to 0, I cannot hear you. Yeah. No, because again, V of t is equal to the integration of the current plus the initial condition for voltage. The initial condition for voltage now for the second phase is this one. For this third phase, it's initially this was my initial condition. For which period? For this period. And then this is my initial condition for this period. Then this is my initial condition for this period. Right? So was this what's confusing? Or was this was the okay? So they also want what? P of t. P is just the multiplication of these two together. So it's going to be what? This is a fixed number, and this is a ramp. So it's going to take this ramp and scale it. So every value here will be multiplied. So you basically take this number and take this number, multiply them by each other, and draw this, right? And then this will be 0 multiplied by this, so it's 0 in this zone. And then same thing, negative number multiplied by this. So take this is a negative number, this is a positive number, so the sum or the multiplication will be a negative number. Then this is a 0 multiplied by whatever is 0, so it's going to look like this, right? Are the values also a problem, or can you calculate the values? Values are okay. So this is P of t, and W is what? W of t is equal to, it's equal to half CV squared, or it's equal to integration of P of t dt, right? So you can either integrate this, so the integration of a ramp is a quadratic, a square, so this will look like, let me draw it in a different color. So it will look like something like this, right? Integration of did we pay attention to? So yeah, P of t is no problem. Yeah, just a multiplication of both of them. Half CV squared. So this is V squared. So the V is a ramp. So squared is this. This is a ramp. So its squared value is also this. This is a fixed value. Squared value is somewhere up here. So you can do it the half CV squared, or you can integrate power. If you're going to do the integration of power, you have to make sure that you do the initial condition thing, right? So you integrated this ramp quadratic value, right? But you don't come back to 0 here because the initial condition is now up here. The initial condition initially was this one, and the initial condition for this part, this zone here, is this point up here. The initial condition for the following zone up here, the last zone is this point here, right? So you can do it either way. I would do the half CV squared. Okay, this is fine. 3.14. You had a problem with 3.16 as well. The same. Okay, so it covers your. Different waveform, but I'm sure. Okay, if you have it, we can do it. Yeah. Goes negative or? Yeah, it goes straight down to a negative. Yeah. Let's do it. Let's do it. But it's a capacitor as well, right? Just a capacitor? Okay, so we have some capacitor here and some V of t and some I of t, and then the current is a square wave. This is I of t. Vc of 0 is 10 volts, right? So again, IC is equal to C dVc by dt, and then Vc is equal to 1 over C integral of IC dt plus initial condition. Okay? They're saying that initially my voltage is 10 volts. This is V of t, right? So this is where I'm starting. And then I do the same thing I was doing before. So voltage is equal to integration of current. So this is going to look like a ramp until this point here, with whatever slope depending on the actual numbers that they use for the capacitor, etc. Right? So this will look like a ramp here. And then this one will also look like a ramp, but a negative ramp, with an initial condition of this voltage. So it should look like this. Yeah. Is this what the answer says? The answer is in your book. Yes, this is what the answer says. For V. Now let's look at P. P is just a multiplication of the two, right? So P of t is, so this until, so it looks like this, right? And then looks like what? Like this, right? You can connect these, so what? No, there's nothing wrong with and then energy is half CV squared, so it's gonna look like like this, like this. Yeah. Okay. Fine. The line, this line here, the negative part. I mean, again, this is a negative number and this is a positive number. Just take these two, multiply them by each other. I mean, it's a negative number or a positive number. It will, you have a negative number. It's a high positive number and a negative number. And then here it's a low positive number and the same negative number. So it's going to be less negative. Okay? Is this fine? Okay. So now let's go back to what we were discussing. So we were discussing this transient response stuff in chapter 4. So again, we really have 4 different possibilities, right? So we have to go back to our equations. We have the following options. We have the RC circuit with a source or without. And we have the RL circuit with a source or without. That's really all we have. We will not do an RL-C combination. So, and the equations that we said, this box that we have in the slide, bring that out and bring out this slide where you have these 2 differential equations in this that in the form of dx by dt is equal to ax plus ax of t equals b or equals 0. Yes, ma'am. Yeah, for steady state, yeah. For steady state, capacitor, open circuit. Inductor, short circuit, solve like you were solving the resistor circuit. right? And then for transient response, these are the 4 options that we have. Bring out these 2 differential equations, bring out the box with the cheat sheets, the results, and then you just apply it like we were doing. So that's really that's to the end of the chapter. That's to the end of the set of slides that we have. We're not going to do anything else besides that. Of course, in addition to the steady state. So we did the steady state stuff, and then we started this. I think we started an example, RC circuit without a DC source, right? So RC circuit without a DC source, we write our equation, our differential equation. Here we have a 0 on this on the right hand side. The solution is in this form. Dig out the box that has the values for K1, K2, and S, and substitute. I can go back and do this. I can go back and on one slide capture that, or I can write them down if you want. Yeah, I'm recording. I recorded the whole thing. Even the solution. Yeah. Okay. That's good. I'm glad it helps you. Yeah. So our cheat sheet box says that solution to this differential equation is in the form of K1 plus K2 e to the st, and the box says that K1 is equal to B over A, and K2 is equal to x of 0, the initial condition, minus B over A, and that S is equal to minus A. This is our A term, and this is our B term. And B is 0, so K1 is 0, that's what we have here. S is minus A, so it's minus 1 over RC, and the initial condition is, they said, I guess, assume that VC of 0 is equal to VI, right? Yeah, the initial condition is 0, so the capacitor is initially charged to VI, so then K2 is equal to VI minus B is 0, so it's VI, so K2 is VI, so we end up with K1 is 0, K2 is VI, e to the S is minus 1 over RC, so VI e to the minus 1 over RCT. We wanted to call RC tau, and it will have unit of, it's sort of like, it will have unit of time, because this is like VI e to the minus t over tau. So tau will have to have unit of time, since it's since you can divide time by it, right? So then just additional terminology that we added to the table here, and then they plotted VI. I think that's what we do next time. And they plotted, sorry, VC. Okay. Right, this is an exponentially decaying, so e to the minus something. It's e to the minus x is a decaying curve. Where does it start? You say it starts from VI, right, and then decays down to 0 at some point. Where does it decay down to 0? You can solve for that. What's more interesting is to solve after one time constant, for example, or after 2 time constants. What is the value of the voltage of the capacitor? Maybe that's what that's what you will be asked. So how do you do that? So if you would like to solve for after one time constant, then you do e to the minus t over tau. Tau is equal to 1 RC. So after one time constant, you have e to the minus 1, since tau is equal to 1 in that case, a one time constant. then e to the minus 1 is equal to 0.368. So after one time constant, the value of voltage on the capacitor is 0.368 times the input, the initial condition voltage. And they're just telling you here that it just happens to be that the slope of this decay intersects the x-axis after one time constant. Just a graphical thing. Okay. Any questions on this? So this is the case without a DC source. The case with a DC source, exact same process, except that we will have a value for B. Right? And here they're telling you that to find current, since you have voltage, IC is equal to C dVc by dt. You do the differentiation of the current like you were doing in this problem 3.14 and 3.16. Right? Can somebody tell me what the current will look like? Yeah. So this is the voltage. So this is the voltage. Current will look like what? Maximum to 0, but it will be exponential, but it e to the minus. So you differentiate this, right? So what's the differentiation of this? Minus 1. It's minus, right? It's e to the minus t over tau. The differentiation of this would be minus 1 over tau, right? Vi e to the minus t over tau. Right? I don't know how exact shape, I don't have it yet. But basically you just differentiate this. You're okay? Why? Starving? I don't have food. I mean, this is... We can change it to cooking class. I don't mind, but... RCU with a DC source. So, again, here, really, nothing... Very similar to what we did before, but we will have a value for B. So, you have your apply Kirchhoff voltage, and then you look at the initial condition. So, as soon as the capacitor is discharged, so VC of 0 is equal to 0. So, my initial condition here is 0, and I have a DC source in the circuit. So, apply Kirchhoff voltage law around the loop. Start from this node. So minus Vs plus R times I. Again, since this is the polarity that was dictated by the text, for example, for C, and it's a passive element, then I know current is flowing in this direction. So you put the same polarity across R. So plus here, then minus here. And that's why you can write the equation in this fashion. So minus Vs plus Ri plus Vc is equal to 0. Right? And then substitute to the relation between voltage and current and write your differential equation. We have a certain format for the differential equation. The differential term cannot have a magnitude, so we divide by the RC, we end up with this format for the differential equation. 1 over RC is A. Vs over RC is B. And then take out your cheat sheet with the values of K1 and K2, because the solution is in the form of K1 plus K2 e to the st. So we solve for K1, we solve for K2. Given the initial conditions, we will have K2 equal to minus Vs. K1 we solve for, B over A, and then S is equal to minus A, so we end up with this equation for this expression for voltage across the capacitor. Okay. Again, current through the capacitor will be the differentiation of that. So in this case, we start with a voltage of 0, and this is a decaying exponential, but with a minus sign, so I flipped it, so it's a charging exponential starting from some initial condition. So the initial condition happened to be 0. The value for this is eventually 0 as well, so that I will finally reach what? I will finally reach Vs. Since this is a decaying term, I know that this will end up being a value of 0, then I will finally reach Vs. And it makes sense. Makes sense. I'm charging a capacitor with a source. At some point, I've charged the capacitor to the same value as the voltage of the source. Two nodes now have the same value of voltage. No more current will flow. That's basically the physical explanation. So any questions on this? So the first term, they call it, they give it the name steady state response because we know that we're going to end up with the value of Vs in steady state, right? In a steady state, capacitor is an open circuit. If the capacitor is an open circuit, what is the voltage across these two terminals? Right? What is the voltage across these two terminals? Remove the capacitor and measure the voltage. Current will not flow, so there will be no voltage drop across the resistor. So the voltage will be the same as Vs in steady state. Right? That's the Thevenin equivalent voltage, if you wish. So, and it's sort of a confirmation for your solution because it tells you that the steady state value for the voltage is going to be Vs, and you calculated this K1 term to be Vs. The second part is the transient response of the circuit. They also call it forced response. But I don't like that. I like transient response. Any questions on this? And same thing here. They also talk about the fact that if the slope of this curve after one time constant gives you a value for capacitor voltage after one time constant. In this case, it's 0.63. So yeah, because it's a certain, we just substitute basically in this equation. So it's RC would be 1, so e to the minus 1 in this case, so it's Vs common factor outside, it's 1 minus 0.368 is 0.6, blah blah blah. So any questions on this? Another example, RC circuit without the source. They give you a value for the R, they give you a value for the C. Find the time at which the voltage across the capacitor reaches 1% of its initial value, right? So nothing different than what we did before. So we have to solve it using the same fashion. So given the as before, so the initial value of the voltage is V input. They give you the initial conditions and find the time at which the voltage across the capacitor reaches 1% of its initial value. So this capacitor is discharging, and they want you to find the time at which the voltage across the capacitor is equal to 0.01 of the input voltage, right? So we have to come up with an expression for the capacitor voltage, equate that to 0.1, and find the corresponding time since we are given R and C. So we do Kirchhoff voltage law around the loop, and then we substitute with the differential, the time varying term that represents the relationship between voltage and current across and through a capacitor. We put the equation in the format that we like. The differential plus A times x of t is equal to b. B here is equal to 0. So now you have your A, you have your B. You know the solution is in the form of k1 plus k2 e to the st. S is equal to minus A. You have your B and your A. You substitute in your equation. That's what they will do here. So we have our equation that we like. This is the format of the solution. K1 is equal to 0 because K1 is equal to B over A. So B is 0. S is equal to minus A, so it's minus 1 over RC since A is equal to 1 over RC. And K2 is equal to the initial condition minus B over A. B is 0, so it's K2 is equal to the initial condition. Initial condition, they told us, is equal to VI. So our solution is the capacitor voltage equal to VI e to the minus T over RC. We equate that solution to 0.01 VI and solve for T. That's what we did here. Okay? We're good? Exact same for the RL circuits. Nothing changes. As if it doesn't exist, right? So the solution, we do the two similar cases. Case with RL circuit without a DC source, and case with RL circuit with a DC source. Same process applies. We have look at their initial condition. So initial condition for current is I of I. And we don't have a source, so the right hand side of my differential equation is equal to 0. You don't even have to go through Kirchhoff voltage law. Just write the differential equation. It's an RL circuit. Same differential equation. So you will automatically write this differential equation, right? This is your RL is A and B is 0. The solution is in the format of K1 plus K2 e to the st. S is equal to minus A. So S is equal to minus R over L. K1 is 0 because K1 is B over A. K2 is initial condition plus minus B over A. So it's initial condition. Initial condition is I of I. So K2 is equal to I of I. K1 is 0. So the expression for current is I of t is equal to I of I e to the minus R over L times t. That's what we have down here. In RL circuits, we define the time constant as L over R, so that we can end up with the same e to the minus t over tau sort of picture, expression. So in that case, tau will be the L over R. So time constant will be here L over R. And the numbers are exactly the same. So after one time constant, e to the minus 1 is 0.368. So you expect that the inductor current, when it is being discharged, it will be 0.368 of its value, of the initial condition. When it's being charged, after one time constant, if the initial condition is I of I, then it will be 0.63 of its value, right? And of course, if we have the current, we differentiate the current and we are able to get the voltage across the inductor. So with a DC source, same process. Given initial condition, we automatically go and write the differential equation that we have down here, right? The R over L is A, Vs over L is P. Substitute in the K1 plus K2 equals K1 plus K2 e to the st equation. S is still equal to minus A. K1 is equal to B over A. K2 is equal to the initial condition minus B over A. Right? So they go through the process on this slide, right? So K1 is equal to B over A. B is Vs over L. A is R over L. Which is equal to Vs over R. S is equal to minus R over L, so it's equal to minus A. RA is equal to R over L here. And initial condition was I of I was my initial condition. So and then K2 is equal to the initial condition minus B over A. B over A was Vs over R. That's the value of K2. So you have now K1, K2, and S. Substitute in the solution. K1 plus K2 e to the st. And this is the expression for current. And then write it in terms of the time constant. So bring the R in the denominator of the denominator, and then you end up with e to the minus t over tau on the right hand side. Any questions on this? I hope I know it may sound redundant, but I just want to make sure I go through the slides. You feel comfortable that we covered the material. Right. So the charging and discharging curves for inductor current. So this is inductor current, assuming the initial condition equal to 0. This will be the current to the inductor. What is the steady state value of curve? Let's go back here. Steady state solution is what? What is the steady state value of inductor current? Yeah, but inductor is a short circuit. So what is the steady state value of current? 100 divided by 50. So it's 50. So we expect that we will have that K1 is equal to 50. That's what we expect to see in our equation. Let's see. Yeah, where is the charging now? These are K1 is expected to be the BS over R, which is the 100 over 50, which is 2, not 50, whatever. My math, I told you my math. I said 100 over 50, right? I cannot divide, but I can put them. Okay, so it's 100 over 50. So this will always be your steady state term. Okay, so it's another check for you. So yeah, so you can plot exponential, given some proper values, then you can draw things to scale. So again, this is an example. RL circuit. There's no need to go through the process of Kirchhoff voltage law, and it's you write the differential equation like we expect it to look like. Apply the K1 plus K2 e to the st, and then substitute with numbers. And then the check would be look at the steady state value of current. Steady state value of current is 100 divided by 50, which is 2 amps. So 2 amps. So yeah, so when you draw your current waveform, it's going to end up going to 2 amps at infinity. How long will it take? Will depend on the value of L and R. The time constant L over R, basically. No, it will be. Steady state it will be 2 amps. No, it will go to 2 amps. It will go to 2 amps. It will keep increasing slowly until it will go to 2 amps. At what value it will go to 2 amps? I mean, you have to calculate the number of time constants. It could be a very large number of time constants. Because e to the minus x can go to 0. Right? So e to the minus x will go to 0 at some point, depending on, or e to the k times x will go to 0 at some point, depending on the value of k. Right? So, and then of course the voltage here, they do the differentiation for you. So you multiply, it's L times the differentiation of the final solution that you have. So this is 0, this is minus 2 times minus 500, minus 2 times minus 500, e to the minus 500t. It's a exponential, decaying exponential in this case, with, again, initial condition equal to 100, since e to the minus 0 goes away with 1, then you end up with starting at 100, decaying to 0 at some time constant. How many? Depends if you're asked. You're probably going to be asked what is the value of voltage or current after a certain number of time constants, similar to the example that we have here. This is a bit different. It looks a little different, but it really isn't. Okay, so what's happening here? Here, for the RL circuit, the switch opens at t equals 0. So at t equals 0, I open the switch. Okay? So let's see what's. Forget about don't look at the numbers now. Initially, the switch is closed. If the switch is closed at steady state, it was closed for a long time. So what was happening? Inductor was a short circuit. So the 2 amps was flowing in the inductor. So I know that the steady state value of inductor current is 2 amps. I know from what I see here. Initial value will be what? What's the initial value for inductor current? The initial value. So initially, when the switch is closed. When the switch is closed initially, what's happening to the circuit? No. Current flows through the short circuit. Right. So this is a short circuit. Initially, you have a current source with a short circuit across it. The current will flow from the current source in the short circuit. Period. Right? And then you will open the switch. If you open the switch, current, this 2 amps, is going to try to flow into this branch and this branch. The inductor will impede the variation of current, right? It will require time for the current to start flowing in the inductor. So what is the initial value of inductor current that we expect? 0. But what is the initial value of resistor current? It's exactly 2 amps. right? So the initial value of resistor current is 2 amps, the initial value of inductor current is 0. And then what's the final value of inductor current? 2 amps, which means that this resistor will have 0 current through it, right? So they're going to swap the current carrying capability. So let's see what we have here. So IL of 0 minus, so right before closing the switch, the inductor had 0 current flowing through it. So because inductors resist the change of current, so the inductor initial condition is 0. Which means that the resistor initial condition for current is equal to 2 amps, because as soon as you have voltage across, you will have current through the resistor. But there's no time required for current to go through a resistor. It's instantaneous. Put V, you get I. Put I, you have V instantaneously. So if I'm putting 2 amps into the circuit, I will have 10 ohms times 2 amps across the resistor. Okay, instantaneously. So IR is equal to 2 amps, and then this is the initial voltage across the resistor, since we just said that it has 2 amps and the value is 10 ohms. This is the initial voltage across the resistor. For as soon as we close the switch, for t is greater than 0, we apply Kirchhoff current law. Kirchhoff current law at this node says that the current 2 amps that is coming in here is equal to IR plus IL. So IR plus IL is equal to 2 amps. IR is equal to the voltage divided by 10 ohms. IL is equal to, again, look at the relationship between voltage and current across, and the VL is equal to L di by dt. So the current is equal to 1 over L integration of the voltage plus the initial condition. Initial condition happens to be 0, right? So this is, the IL of t is equal to this. And then we substitute with this and that in the Kirchhoff current law equation, so we end up with this equation. Now we want to push this to make this, put it in the form of this differential that we came up with before. So differentiate the equation, you will end up with dV by dt. So you differentiate this, so 1 over 10 goes outside, and you differentiate the voltage with respect to time. And then this is an integration, so when you, the integration where you differentiate it becomes a differentiation basically. It becomes the constant, the value, the v of t, the variable that you're trying to integrate here. So you end up with this expression. Again, we don't like it. It's still not in the form that we like. We have to bring the remove this 1/10 from here. So multiply by 10. Multiply by 10. You end up with a 5 here. There's a 0 on this side. So you end up with the differential equation that we like to see. 5 is A, B is 0, S is equal to minus 5, and you just substitute in the K1 plus K2 equation. That wraps up this chapter, really. So any questions on this transient response? It's not in the exam. This is chapter 4, right? You said it's only chapter 3. 1 to 3. Yeah, it's not in the exam, but it will be in your quiz. I think it's in the coming quiz, because this last homework has a lot of chapter 3, but it also has a few chapter 4 things. So hopefully it's not too hard. Yeah. So I'm not gonna start something new. So the next chapter is what? Sinusoidal analysis. So we've been talking about DC sources before. What we will do is go through very similar things, but with an AC source. We'll leave that till next class.